I'm Dave DeMarle. I work at Kitware. And if you would like to follow along with the exercises in here, get some hands-on practice, you'll need ParaView 561, which you can get off of paraview.org. Okay. Go back to the beginning of this. I'll get started here. Before I do, a little bit of advertising for Kitware. It's kind of mandated. We're a small company, about 180 people right now. We've got 5 offices, 4 in the US and 1 in Lyon. And we do open source software. We have expertise in things like computer vision. These are the people who write software which derives meaning from videos and pictures. I work in HPC and visualization, so scientific visualization. It's the core of the company. It's the oldest and I'd say best part of the process that we work in. We do medical computing and software process as well. The computer vision department, they primarily do DoD projects. As I said, we've got an open source project called Quiver for doing image analysis and video analysis. They do the opposite of what I do. I take data and make pictures. They take pictures and derive data from them. As I said, I work in HPC and visualization. We are the primary authors of VGA and ParaView, which Joe mentioned earlier. VGA is a library for producing pictures and analyses of scientific data sets. We're also well known for software process. We're the people behind CMake and related projects. Again, we write open source software and we release it to the world, and our business proposition is that by consulting with us, you can save your own time and make it worthwhile to work with us. Because we can teach you to use the software faster, and we can make it do new things faster for you or with you, and you'll save your development time. Company is about 20 years old, so we're doing okay. ParaView is the focus of this talk. It's an open source application and software library environment. It works on Windows, Mac, Linux, HPC environments, of course. And one of its selling factors is that it supports distributed memory computation. So it's scalable to extremely high resolution mesh sizes because we can split up the data among the memory of the many nodes in a cluster and work and produce results and pictures from this split up representation of the data. It's one of our flagship projects. It's been developed for quite a while now. It's got many different aspects, guises to it. I'll be taking you through the desktop interface to ParaView. There's also ParaView Web, so there's ways to run ParaView on the web, either server-side or client-side. There's Python scripting, which Joe alluded to, and I'll take you through shortly, including some people have done Jupyter Notebook integration with ParaView. It supports immersive environments, both cave systems and head-mounted displays fairly easily. And of course, it runs on large computers. Sorry, Argonne folks, for not putting Theta up here, but the slides are a little dated. Okay. And I'll get in the end to the in situ capabilities that Silvio talked about. So when I say it's scalable, what am I talking about? So these are some of the past landmarks for the ParaView usage. Back in 2005, it was a big deal to do 6 billion structured cells. Now these days, you can do 6 billion cells in structured format on a decent desktop. Wouldn't be too problematic. A more recent benchmark result was before Lanel's Trinity machine went from the yellow open science period until the red. We were involved in making sure that ParaView and CMake and everything ran on the machine well. And on a tenth of the machine, we were able to do a scaling run of 1.1 trillion unstructured cells. So it's good for really large data. Yes?
What do you mean with having this large data? Producing filter on that, or just loading the data
Filtering, so loading the data, filtering, and rendering.
Okay, so with no heavy computation like streamlining on the data.
Some of that, one of the secrets of Viz is that most of the algorithms we apply are pretty cheap. So yeah, you can streamline and work on big data sets like that. Unstructured is particularly challenging because there's more memory and because there's the topology which you have to work through. So it's much harder, which is why we've split these up into structured and unstructured. But certainly you can at LANL, on Trinity, they work day to day with more than 1 trillion elements and are able to use it. Okay. So this is a not very impressive picture. This is what the benchmark looked like on the machine. It's not too impressive until you look at the Moire patterns, and if you focus in very closely, you can see that these are little circles or little spheres. Each one of those spheres has 1 million polygons in it, so it's pretty scalable. Okay. ParaView is an application built on top of VTK, as Joe mentioned. We have the VTK layer, which does all the hardcore rendering and processing, and the parallel structures are built in at the VTK level. On top of that, we have a server or server manager level, which is where we add the distributed client server capabilities that we build the ParaView application out of. Mostly out of things which are already available at the VTK layer, but we package them all together. And then we add Qt widgets to make a nice package that you'll be playing with shortly. And out of that, we've structured the CMake build system so that you can rebrand ParaView and use it and build different applications out of it. Okay. So this is in one slide what Joe was saying. Scientific visualization is the process of taking all some numbers, scientific visualization, so these are numbers which have some natural embedding in a 3D or 4D world, and then producing pictures, primarily pictures and graphs out of it, because the human's highest bandwidth interface to our brain is through our eyes. So you make a picture, and then, as they say, a picture is worth 1,000 words. To become expert in ParaView, it helps to know a little bit about VTK. These are kind of the core data structures in VTK, all the core data structures for representing 3-dimensional data. There's uniform rectilinear, so completely regular, doesn't take a lot of space to represent the geometry or the topology for this, just 32 bytes. And then all the rest of the data of the memory for attribute arrays. So the values in this regularly sampled space. All the way up to increasing the degrees of freedom through semi-regular, all the way up to unstructured grid, which is completely free format, anything you can represent with a set of points in space and the connections between the points. So the geometry and the topology, or the points in the cells, or the nodes and the elements, depending on which background you're coming from. And then out of these, we have auxiliary data structures that we use quite a lot. Composite data sets for representing complex objects or parallel objects. And we have things like AMR and tables and graphs, but the tables and graphs aren't as well used in most ParaView day-to-day environments. Okay. So is everyone with me? Everyone's looking a little dazed after all the talks so far? We're okay so far? Okay. So if you start up ParaView and go to the help menu, you'll see that we have a reasonably complete help system. This is in contrast to ParaView version 2, where you'd pop up the help menu, or you'd hit the help button and it would say buy a book from Kitware. We've spent a lot of effort in making it somewhat approachable. It's a complex piece of software, but we really do want to make it usable. Some of the most important help features in the application under the help menu, there's a getting started guide, which is a two or three page PDF file, which tells you a lot of what I'm about to tell you now, just kind of core familiarity with ParaView, enough to get you up and running quickly. There is a link there to the ParaView tutorial, which most of these slides were ripped from and condensed out of. That's the day-long tutorial that we've given many times at supercomputing and other conferences, which is a very complete introduction to using ParaView. There's the slides, and there's also a pretty well thought out PDF document that go along with them. There's also a link to the book. It's free. You don't have to buy it anymore. You can, but you don't have to. There's a link to the guide in the help system, and you can just download it and look through it. That's also pretty well written. And two of the most useful resources available to you. This is open source software, so you've got a large community of users and developers. You can reach them all through the ParaView webpage or through the ParaView Discourse forum. We've recently moved from email to a Discourse, a web forum. So go to discourse.paraview.org. And there's a lot of generally friendly people there who will try to help you. Besides the help menu, things to be aware of is we have pop-ups. So if you leave your mouse over somewhere on the UI, generally a little bit of help text will pop up to tell you what this thing is for. Try to get you going. And also be on the lookout for the question mark icon. You hit that and it'll pop up with a page which is somewhat relevant to what you're working on. Okay. When you do start ParaView, you get this large gray blob with several sections on it. There are a lot of icons centered in the toolbars along the top. These are all all of these icons are conveniences. So you can get to the functionality behind any one of these icons somewhere else buried in the GUI, but these are the things that people frequently do, so we put them on top of the design so that you can get to them quickly. Okay. So we've got a menu bar where you say File, Open. You can open up a data set. File, Save Image to save an image. Export a scene, export data, all through the File menu. The Help system we've talked about. Links to Catalyst, and the one most important content in the menu bar is the Filters menu. Okay. So the toolbars, as I said, has icons and links to things that you'll find elsewhere, but these are echoed, mirrored there for convenience sake. To the lower right side is the View section, which is where you will have images of your data. Okay. We'll talk about these a little later. You can have 3D views like we're seeing here, or you can have plot views, or multiple of these, and you can link views together to keep the camera oriented consistently. On the left side, we have something called the pipeline browser. This is the core data processing and rendering that goes on behind the scenes in ParaView to take in some data and present you some result that you see in the right. So it's the structure of this DAG of processing operations, starting usually with one or more readers. Okay. Beneath the pipeline browser section is the Properties panel, which has two important sections on it. The Properties tab shows you all the controls you have for the currently selected item in the pipeline browser. Okay, so it's very context sensitive. Likewise, the Information tab shows you metadata about the data being produced by the currently active option in the pipeline browser. Under the View menu, there's a bunch there. Under the View menu, you have links to open up these, close these, show more obscure view types, close menu bars, and so forth. It's all modern Qt, so we can move things about to suit your purposes. If you want to get back to the initial state, you can go to the View menu, hit F11. It'll give you a full screen view of just the data, so hide all the GUI components. So who all has ParaView downloaded? Okay, great. So go to the Sources menu and select the cylinder. And we're not going to load some data off disk right yet. We're just going to generate something. This as a means to get familiar. And once you select the source, you generally will see no change. other than this menu, this button, green button or blue button, depending on your operating system, will be emphasized on the Properties tab. And you don't actually see anything until you hit that Apply button. Okay? That is by design. ParaView is built and meant for this very large data, for which any single operation, like loading a terabyte of data off disk, might take a while. So ParaView gives you a chance to decide whether or not you actually want to go through something or not. Okay, so that's what the Apply button is for. If you're working with small data, you can, and it doesn't really, and that doesn't make sense for your workflow, you can go to the Preferences system and turn on Auto Apply and get rid of that behavior. Then whatever you do will take effect immediately. Okay. So do people have a picture of something that looks like a very bad cylinder in the right? Okay. Above the view, you'll find these icons, if your eyesight is fairly good. These are all about controlling the viewpoint. Okay? So you can drag the mouse in the view and change the camera position. I think shift and drag will pan, maybe, or maybe I've just always set that up in my preferences. Might roll. Under the preferences, you can control what shift mouse and control mouse and alt mouse all do. But you can move around the camera at will with the mouse in the view, or you can specify, or you can choose canonical views from these icons in the toolbar. Of these, I find the most useful is this X button, which says reset the camera in the view such that all of the data which is visible is more or less centered and scaled to fit in the screen. So you often find yourself hitting this button over here to kind of get yourself to a default good view. Okay. The cylinder doesn't look very good because by default we started with a very low resolution. But we can change parameters kind of anywhere on the visualization pipeline on the Properties panel. So go to click the source in the pipeline view to make it active. We only have one thing there so far, other than the server we're connected to built in. And then increase the resolution of the cylinder. And then again, hit the Apply button. Okay, now it should look more like a cylinder because we've generated some new data and we've increased the resolution of this mesh. Okay. Things to be aware of, I've told you about the Apply. There's also the Reset button, which resets if you're in the middle of making a change to some property and you don't want to take effect, you want to go back to what you had before, you can hit Reset. If the element in the pipeline you're working with is a leaf node, you can delete the element. Okay. And you can also do things like copy and paste settings on any object. You could save them in your preferences so that the next time you create a cylinder, because we all do that all the time, it will be a higher resolution by default. You can do that type of thing, and so forth. Underneath, so I told you about the Properties panel. The top section, you can close these. The top section in the Properties panel is all about the properties of the object. In this case, we have a procedural sphere mesh generator. We can control the origin of this and the resolution on the top section of the properties. Yes, go ahead.
About saving, does that save it through all sessions, or will it reset when you close ParaView, or does it
So when you save the preferences, your property settings, it saves it in your local preferences. So the next time you start ParaView, it'll start up. You'll get the same thing.
You'll get the thing that you saved.
Yes.
Okay.
Yeah, the settings that you saved. For saving the entire workflow, so this sphere and all your pipeline, you go through something called saving state, which we talked to earlier. Say the file menu, save state. That will save your entire workflow. so that you could just load the state next time you start up and you get back to where you were. Okay. So underneath the controls of the object, you have another section which controls the appearance of that object. Okay. You'll see things here like turning on specular highlighting to make an object shinier or not. Controlling the color. Right now we have a very gray cylinder and a dark gray background with a gray application. You can change on the color section, you can change it to a different color. Okay, so on the display section of the properties panel, you have all the controls for how an object looks in a view. Okay. And the most important of these settings, like the color and the representation, whether you're looking at the surface or the surface plus the edges to see the kind of the mesh or volume rendering, these are all echoed on the top in the toolbars again. So go ahead and change the color of the cylinder, make it something not quite so ugly and gray. There is a third section within the properties panel, which is the view section. So as we can control the appearance of an object in a view, we can control the appearance of the overall view as well if we navigate further down on this panel to the view section. Things we can do here are change the entire view, like change the background color. We have this gray, which we chose because it's not likely to appear in your lookup table. Makes everything else stand out, and it's neutral. It's not black or white, but you can change the color however you like on the view section. Okay. You can turn on single color. If you turn on gradient, let me see. So if I have ParaView here, source, not very cylindrical. So I've got the Properties tab. On the top, I've got a section for the characteristics of the object, the resolution and such. Beneath that, I've got a section for the appearance of the object. I'll change this to surface with edges, or echoed up here. Okay. Outline, if the data is really, really large, this comes in handy at times. It's good for showing context. And beneath the display section, I have the view properties. And I am going to, I didn't tell you about the gear icon yet. This changes from the usual properties to the advanced properties. And under here, I can change the background color to something else or some things else. And I can load images to use as a backplane. Okay. So on the bottom of the Properties tab, you have View Appearance Controls. Above that is Display Controls, and above that is Controls of an Object. Okay. So it's under the View, and you may have to press this gear icon up here. Another thing you can do is say search, because there's an awful lot of controls here. It's useful to just type in a few strings. Okay. Okay. So another control that's useful, you can turn on axis grids, so you can have the extent of an object shown as text. So go ahead and turn on the axis grid and see what that looks like. And this gets back to your question. I should have had this slide up much further, much further ahead, but there's a lot of controls. It's a complex piece of software with many, many options, and our goal is to provide as many options as we can. That makes it confusing and making a easy to use GUI challenging. Our current approach is to separate these controls into advanced and frontline. And if you hit the gear on any panel, you'll get the advanced options. So if you don't see something, hit the gear, you'll probably find it, or use search. Okay. Another key feature is that we have a full undo redo stack. I mentioned briefly about the reset. That only applies in between actions of apply, but you can go all the way back to the beginning of session if you like by looking for these undo and redo buttons. We've separated them into camera controls because it's often the case where you move the camera to something that looks just right, and then you move something and you kind of lose that perspective. You can get back to that with a camera, redo and undo, or you can save that if you need to in a macro and so forth. Okay. So that's kind of the key feeling for how to use ParaView. So you at least have some context for what these guys are. Let's start working with some actual real data. As Joe said earlier, ParaView and Visit and VGA have many, many file formats. One way to get a list of them is to say File Open, and then browse the list of extensions. That'll tell you what your current copy of ParaView is capable of loading at that moment. Some of the more popular ones are Insight, the VTP and VTK file formats. These are ParaView or Kitware specific file formats. And the XDMF, which is a wrapper around HDF5. It's an XML wrapper which describes the content of an HDF5 file. The many others here. Okay. And of course, you can extend ParaView as Joe talked about earlier. You can either have C++ libraries that you load at runtime, which extend the functionality. A popular way, one of the popular types of plugins is a file reader plugin. So if you have some custom format that you can't deploy outside of your institution, you can write a plugin for it and distribute that within your institution, and then everyone there will be able to load this plugin and open up your data and work with it. And there's other types of plugins. So a plugin is a C++ compiled library which has to match our build. If you're using a Kitware provided binary, you have to make sure the compiler and options all match up. But it's often easier, especially when you're doing quick development, to extend ParaView with Python scripting. Since ParaView 5.5.2, the best way to do this is with annotated Python scripts, which you load through the Tools Plugins menu. This is just Python code. In the case of a reader, it's Python code which knows how to open up some file and create VTK data structures of those 5 primary types we talked earlier, with a little bit of Python decorators to tell the ParaView GUI what it should do with this bit of code. So the takeaway point of these 3 slides is that we support a lot of different file formats, and then you can extend ParaView in kind of different ways to bring in other file formats. Okay? And if the data you work with is not supported by ParaView, ask on Discourse. It's likely that someone else in the community has worked with it. If not, you can write your own, or you could ask us and we can help you write it. So let's practice. Go reset your ParaView session or close and open it. If you haven't found the reset button, which is the top left, it's this button up here, reset session. And if you would, load one of the data sets that we provided with the ParaView binary. So if you navigate to your ParaView application, wherever that may be, there will be an examples directory somewhere there.
There's a shortcut on the left.
I'm sorry?
There's a shortcut on the left.
Oh, yes. Yeah, we could do that. And because I've opened it recently, but if not. Okay, and then open that and hit the apply button, and you'll get another cylinder. Another gray cylinder. This one is slightly more interesting. This is an Exodus file produced at Sandia probably 120 years ago. It's very small. This is not just a surface mesh, as we were working with before, but it's actually a volumetric mesh. What this data is from is a simulation where they had a disk in the center of the cylindrical space, which was heated and spinning. And the rest of the volume that you see here is the fluid, the air and other gases, moving in reaction to this heated and spinning cylinder. Okay. When you load it, doesn't matter if you've hit apply yet or not. Exodus files, we work with them frequently. You can have any number of data attributes on the nodes or the elements, on the cells or the points or the cells. One way of working with large data is restricting the arrays that you have in memory at any time. And the Exodus reader lets you pick from the available arrays before you load the data or afterwards. So that's what this variables selection lets you do on the properties for the reader. Okay. Do people see this, the variable selection? Okay. So it's a small data set. Open up all the variables. Click here, and it will toggle them all on or off, and you can load individual ones. And then hit apply. And the appearance won't change all that much. But you can color by the different quantities here. Okay. I talked about this earlier. You have kind of really fine control over the appearance of the object, either on the display section of the properties panel or use the conveniences and the toolbars. You can pick fundamentally different representations. So this is the surface representation we've been seeing. Here is a point representation just showing the external points on the data. The volume rendering is a different representation you can choose. A few other more arcane ones. You can choose the variable that you want to color by, which is what I was doing. And if the variable happens to be non-scalar, you can pick a particular component to color or use the vector magnitude to map through the lookup table. And to the left, you can do tricks with the color map. You can turn on and off the color legend. You can edit the colors or load different color lookup tables. You can go back to a rainbow color map, but I highly recommend against doing that because I know, but it's fun. But I like to be able to say the rainbow. One of the reasons why the rainbow color map is bad is because it looks like clown vomit. So it's just garish. It lies in all kinds of ways. So the ParaView one is pretty good. And then you can control how the colors change, if so, over time. Yes?
This is a super detailed question.
Uh-huh.
How do you delete if you accidentally added a point onto your little color thing? How do you get rid of it?
I think you can select it and then hit the delete button. I think that will go away. It didn't do it. Try control delete maybe. I'm not sure. Got it? Okay. Yeah, just jam it buttons. You'll get to it eventually. That's how I use ParaView. Okay. So we've loaded up an object so we can have some real data, and we've controlled the appearance of it. But ParaView's real strength is that it's very, very flexible. We've chosen to expose the VTK processing pipeline to kind of give you the full power that we can of the data processing options that VTK gives you. In VTK, there's something like, actually there's, at last count, there were 782 distinct filters. We've exposed about 140 of them in ParaView, which are known to work well in parallel. And these are the most common ones, the ones that people use all the time. You'll find these on the toolbar section. There are things like applying an isocontour, as Joe talked about, clipping, warping the geometry according to a vector or a scalar field, applying streamlines, inserting glyphs into the data, thresholding, subsetting if you have image data. So these are kind of the bread and butter visualization filters. Okay. You'll find the full list of them under the filters menu under the alphabetical list, or you can see them grouped by purpose or domain. So the subset of filters which are really good for processing time-varying data are under the temporal list. The data analysis filters, things like plotting and statistical analysis, you'll find under data analysis. The common are exactly those set that I showed you the shortcuts for. Or hit search, and it'll pop up a dialog. You type in a couple of letters from the name of a filter or an operation you're trying to do, and it'll pop up. It'll give you that list of filters which match that. It's kind of the fastest way to look through them. Got about 150 built in the copies of ParaView that Kitware distributes. As before, with the readers, you can extend ParaView with new filter types, either via C++ plugins or Python algorithms and filters, which you can do at runtime if you're familiar with VGA Library. This is quick launch, as I said before. It's just a way to search through the whole list of filters and sources. It's control space on Mac and Linux and alt space on Mac. Sorry, on Windows and Linux and alt space on Mac. Okay. So reset if you have to, open up disk out ref, load all the variables and apply the contour filter. And furthermore, choose to extract the ISO contour of the temperature array in the data and choose ISO value 400 degrees Kelvin in this case. Okay. And you note that there's very little mention about units. ParaView and VTK are expressly unitless, so we're just doing the manipulation. We're not trying to do the work of converting the units and keep them right. That's kind of up to you, unfortunately. Okay. Okay. And you should get something that looks like this. So I've opened up the disk out ref. I've made sure I have all the variables loaded. I'm ISO contouring, and I don't want to contour by ash 3. I want to do temperature. And I want to choose a temperature which is in the min and max value range present. Default is not within that because we had a different attribute at first. So I'll delete this, make a new one at 400 degrees, and hit apply. And now I have an object which looks like half an egg. Other things you can do here, rather than the ISO contour filter can extract a bunch of ISO contours at the same time. It's not really interesting in this data, but if you look carefully, you can see I selected 10 different ISO contours. And if I color by temperature, say compute scalars to do this, and then compute color by temperature, you can see that I've got a bunch of shells that all match the different values with or locus of points within the data, which have a set of temperature values. So we got real high, real low. Get rid of all of these, go back to 400, and apply. And now I have just one value, one isocontour within this 3D data set. Okay. If I want to see this in context with the entire data, I can hit this eye icon up here on the data that I read in from disk and make that visible. But that's not particularly useful. So I'll change this to something like outline. And then hit the reset camera, and I can see that this set of points was located within the data, roughly halfway in the middle. Or change the representation of the data I read in to surface with edges, and then change the opacity. Hopefully. Oh, okay. Make that active. I'm sorry? It's in display, thank you. And then change opacity, make it very clear, and I can see this region within the data. Okay, so I can get some context. Okay, so that's one filter. We have 150 more to go. Okay. Let's try another one. Let's make a branching pipeline. Okay. So one of the things, if we're paying close attention, what I did there is I wanted to change the appearance of the reader. So I went to the pipeline browser and I clicked on the reader, the disk out ref. That made it active. So do that. Click disk out ref. And then apply the extract surface filter. Okay. And I'm probably going to get going faster and faster, but all these slides are available online in the ParaView tutorial. You can get to them. But I want to get you at least familiar with the core things so that you can start working with ParaView on your own next. Okay. Furthermore, once we've extracted surface of the data that we've read in, apply a clip filter, and then we should have a branching pipeline.
Where's extract surface?
In filters, you could go under alphabetical, or use the quick launch, which is Control space or Alt space. Okay. One of the options for this clip filter is called show plane. You can enter the plane equation for this clipping plane on the properties panel in text mode. Or you can use a widget, a 3D widget in the view, and just click and drag this slice plane around. In either case, once you've got some setting, you generally don't want to see that widget anymore. So if on the Properties tab you turn off Show Plane, then that goes out of that goes out of the view, and you're just seeing the output of the filter. Yes?
For the quick launch, a few of us, when we do Alt space, we just get a box that's just empty. You can't search anything.
Okay. Did you so after that came up, click on it to make it active, and maybe the window manager, and then start typing letters in there?
It's like it's a box like this.
Yes.
And then they're like just empty parens, and then a thing that's like a button you can click that has nothing in it, and then what looks like a text field that you can't click on. So like the only clickable thing. Yeah, that.
Oh, okay. Okay.
Wait, what the heck did you just do?
So I just started typing. It's just, like I said before, just randomly hit keys, and it'll usually work out. Yes. Yeah. That is quite confusing. Yeah. Yeah, it's a quite complex piece of software, and we're trying to make it really like expressive and powerful. But it's an open challenge how to make something which is like very expressive and powerful also easy to use. So we are wide open to suggestions on making this better. So, okay. Okay. And then what you should get is, so what we've now done is we've created a branching pipeline. Okay. So we have the data being read in from disk. We're, at the same time, we're extracting an ISO contour, and we're applying kind of arbitrary other operations on this. Okay. So one of the real strengths is that you can combine these filters together in kind of new ways, whatever suits your fancy, to drill down to get to the data, to the results that you need, to the images that you want, and so forth. But that's kind of the method of ParaView, is to expose all the options to you, and then try to help you get the best use out of it. Okay. I alluded to this earlier. These eye icons on the left of the pipeline browser, these are how you make something visible or not visible. That in itself is a shortcut to the visibility parameter on the display section. Okay. So you don't have to use the eye icons. You'll find a control on the display section of the properties tab, which makes things visible or not visible, but this is kind of make the easiest way to go about hiding or showing something. And as I said before, the ParaView is very context sensitive. The controls that you see on the properties tab are tuned, they reflect the currently active item of the pipeline browser. So this is the ParaView GUI. Pretty much everything you can do in ParaView GUI, you can also do from Python. Okay? And the best way to learn how to do something in Python scripting for ParaView is using trace functionality within the GUI. So reset ParaView, and then go to the Tools menu and say Start Trace. And furthermore, click the Show Incremental Trace. And then hit OK. So open up, I said can here, that's a typo, I meant disk out ref. Apply some filter. Now if you hit the show incremental trace, you should have a text window popping up. These are the Python commands you would use to do these, that you can use to do these actions that you're taking in the GUI. So while you've got the trace on, everything you're doing in the GUI is being translated into Python, and you're seeing it. Question? You guys okay? So I'm sorry, I said can data set, I meant disk out ref. Can be anything really. When you've got things set up the way you want, say go to Tools and Stop Trace.
You say you meant disk out?
Yeah, I meant disk out ref, not can, sorry. Either one will be fine, but.
So we have some pre-existing thing that we'd like a script to do, but we forgot to start the trace. So
Yep. You can do that too. So in the File menu, there is a Save State. And there's two different file formats in there. One is an XML, it's called PVSM. The other one is Python. And so that one will also work. But the saving trace is quite useful for learning about the scripting API. Okay. So after you've saved your Python script, reset ParaView, and again go to the View menu and open up and choose Python shell. Okay. And what this brings up is a window which has a Python interpreter in it with all of ParaView's bindings turned on. And one of the really nice features about this interpreter is that it's linked to the ParaView GUI. So things you do in the GUI you can get access to, and vice versa. And the other really nice thing about it is it has tab completion. So another useful thing to know about when you're trying to learn ParaView Python scripting. But then once you've saved your script, in the Python shell, there's a button that says Run Script. Click that and navigate to wherever you saved the file, and it should pop up with more or less what you had previously. There are other ways to do this. You can save them as macros, and they show up as buttons. You can run an executable that we deliver called PV Batch, which is ParaView's server components wrapped with MPI and Python. And that's kind of the key to doing real scalable processing in ParaView, is to save off what you want to do as a Python script and then submit it through the queuing system. And inside your job run is going to essentially be MPI exec or AP run, some number of processors, and then PV batch executable, and then the script. Okay. So besides scalability, the other aspect that's really nice about Python is it's inherently reproducible. So you don't have to rely on clicking the same places over and over. You just run the script. So far, we've only seen one view, one render view. This is what ParaView, the interface was like back in ParaView 2 about 12 years ago. And ParaView 3, we added multi-view. And we came up with a splitting metaphor, GUI metaphor, for creating new views. So up on the top right of the view, there's a set of buttons up there. The two on the left are essentially split view along the horizontal or vertical. And once you do that, in the space that's created, you have a menu for what type of view do you want to create. There's about 10 or 12 of them. The render view is the one we've been working with. And I'll demonstrate here to save some time. So I want to hide this guy, and I'm going to split the view, create a new render view, and I'll make the contour visible in both of these views. But in the one on the right, I'm going to color by the pressure. And in the one on the left, I'm going to color by the magnitude of the normals, which is essentially noise. I'll say X component of the normals. Okay. So one thing that's going on here is that I've mentioned that ParaView is context sensitive. The elements in the properties tab depend on what you've made active in the pipeline browser. It's also context sensitive in terms of the view. So the controls that I have on the display section for the contour in this view, it's saying that I'm coloring by pressure here. And on the left now, it's saying I'm coloring by normals. Okay, so it's quite context sensitive. Yes?
Do you have the same pipeline in both?
Yes. We've got one pipeline that we're showing in all of the views. Okay. That pipeline, it doesn't have to have a single root, though. You can open up multiple data files and create independent pipelines if you want to. But it's kind of going against the grain. Okay. Something that's useful is, so now we're seeing the same data colored by different things, so we can kind of look at the interplay between these two different variables on the data. It's not a great comparison because I'm kind of manually moving the camera here. I could use these shortcuts to get a consistent view, or more conveniently, I could, if I remember the key, stabbing it. Stabbing keys. So I should be able to right-click on one of these views but it's not working for me for some reason.
Is it link cam?
Yeah, and say link camera. I think I'm in a weird state where it thinks I'm pressing the mouse all the time. No. Let's say file, save state. And then reset. And then file, load state. State 1. Sure, I'm going to load the state, and it's giving me the option to, I may be loading the state on a different computer where the file system is totally different. It gives me some options for how do I navigate to the files on disk to load. This case, I'm on the same machine, so I'll just use the same names exactly. Okay, and now I should be able to right-click, or not. It's not working for me, so what I'll do is I go to Tools and say Add Camera Link. And click on the other view, and now anytime I make a change in the camera on one view, I have the same settings on the other. Okay. Okay, does everyone have multi-views to kind of know what I mean by them so far? Okay. Joe, you okay? Yeah, okay, good. Okay, so now let's do some more interesting processing, okay? So we'll reset ParaView, and let's do some stream tracing. So what this is going to do is, this is a filter which drops, it starts at some locations in space within the data, and then it will, so it's going to drop these particles into the volume, and then it's going to advect from these particle locations according to the magnitude and direction of some vector field to create, over time, a path, which shows you the path a massless particle would take in this vector field. Okay, so we'll use the stream tracer and change from the first choice on the stream tracer is how do we want to put these points into space? The default is to use a point, segmented a line segment in space with 100 different points along it. Let's change that to a sphere centered around a point. So on the stream tracer, change the seed type to point source. And then hide the sphere, because we don't care to see where these points are starting from. And then hit apply. And then these points, when you first create them, they're kind of hard to see. You can't really see any depth information about them because these are infinitely thin points, infinitely thin line segments. I don't want the glyph. I want in my case, I open up the data and I can't apply the stream tracer because the data by default doesn't have any vector fields. It's just a mesh. But once I turn all the variables on and hit apply, then I can apply the stream tracer. And if I hit apply, it calculates there, and then it drops these points in space along this line, and then moves along the vector field for them. So the results vary depending on where I have these points in space to begin with. I'm going to change this from a line source to a point source. And then I'll hide the sphere and reset the camera. And so this doesn't look it's not very understandable because these infinitely thin line segments don't have any normal information, so we don't get any lighting cues. So one thing you can do about that is apply a filter. So I'll apply the tube filter, And this will kind of give them some extent, and then I can use lighting cues that I expect to see in a 3D world. Okay. So now I can see that in this data set, the overall organization of the vector field kind of moves up or down, I can't tell yet, along this central column, out and down on the sides, and then in the center, it kind of moves around in a spiral. Yes?
Yeah, but the data main width actually has a variable to separate the components for the vector. Can you create a vector inside?
Yes, you can. One way to do that is up here we have the calculator filter, which you could type an expression using I hat, J hat, K hat to bring 3 scalar fields together into a vector field, so you can construct it that way. A better way would be to use the data analysis. Let me see the Python calculator. I'm not seeing it here. Filters, search, Python calculator, and then in here I can put in an expression, the syntax of which I don't recall right now. It might be just if this is one attribute, it may be this. I'll have to work it out later.
How do you get that?
So this was the Python calculator. So it's a filter. I'll probably have to play with the expression to bring it up to the top of my head. But then with the tube, we can see that the data at the bottom kind of moves in this spiral, which is what you'd expect because this is a spinning cylinder. So it's kind of moving along the direction of rotation. Okay. And then continuing on, gotcha. Yes, question?
The sources, so the sources for the streamlines in the source for the streamlines. Is it randomly done?
In this case, so what we did, so go back to the stream tracer and click back on show sphere.
And how do you put the sources for the streamlines in there?
So in this case, we're just taking this sphere, and on each of these points, that's the starting point. We can move this around and move them. We can change the resolution, stuff like that. The line source is a little more reproducible. Or there is an alternate filter called stream tracer with custom source. So if you create some shape, so a plane, what I've done a number of times, or I could load in some shape or create it in Python, and then I can use that as the starting locations to add vect along. Okay, so you can get much better, finer control than I'm showing here. Okay.
And which integrator should they use for the streamlines?
The default is usually pretty good. There's several different integration options, which I don't know the differences for. On the help, it probably shows you what they mean, the integration, the specific integration kernel. If not, you can ask Discourse, and we have the sources available too, so you can look there.
And the streamlines suddenly add if I do a length scale longer than count plus reason for that.
I'm not exactly. I'm not intimately familiar with the details of how they add vect along, but it's possible that they step off the data and then they stop. Is one thing that can happen. The step size can vary in different ways based on the integration kernel and the data, but I don't know the specifics of them yet. We can talk later, or we can ask on Discourse. Okay. Yes?
So for the tube filter,
Mm-hmm.
is it possible to use different cross-sections?
Yes, you can. So the tube filter can, one of the so the place you look for this would be on the Properties tab. And we have, maybe it's an advanced property. Vary radius, turn it on by a scalar or a vector. So we have a tube filter, and it's just, but the default option is we're going to have them exactly this wide and this many sizes. But
I wanted like a render like a beam cross-section or
possibly. We can talk about it later. Okay. Okay, so I have the stream tracer here. So other things you can do. So we have the stream tracer and we had the tube filter. Change this back to point source. Okay, I've got this. So we wanted to actually figure out which direction these guys are moving. Change this to I'm going to reset here to get back to a kind of known state. Okay, so we see the overall shape, but we don't really see the direction yet. We can do more. So let's use another vector viz technique. I make the stream tracer the active item in the pipeline browser, and I'm going to insert some glyphs. Okay, and I'm going to change these glyphs from being arrows to being cones. And I'm going to orient them along the velocity field. And then I'm going to change the scaling to be more sensible. And then I'll change the color of these guys to make them colored by, let's see, integration time. So the integration time is the length along the advected field. And I can generally see that the vector field is starting at the disk, and then it moves up through the center. Okay, things get cool, and then they come back down. So by playing with the visual parameters and the pipeline parameters themselves, you have quite a lot of power at your disposal to introspect the data and kind of query what's going on. Okay. You can get even fancier. This is some work I've done over the past couple of years. So far, we've been doing OpenGL rasterization. For the past couple of releases, we have a ray tracer. We have a couple of ray tracers now. On the very bottom of the view panel, turn on Osprey. So that tells the view, don't use OpenGL rasterization to render this data. Use a ray tracer and tells Osprey that Joe and Silvio talked about earlier. And then turn on shadows. Okay. So Osprey is on the very bottom of the view section. It's becoming less experimental, so I'd probably move that up at some point. So I'm just showing the stream tracer directly and the glyphs. And I'm going to the very bottom of the view, very bottom section of the Properties tab under the View, and I'll turn on Osprey. Now I'm using a ray tracer.
What version was Osprey added in?
Osprey was added in 5.0 was the initial one. We've had kind of major improvements at every release since 5.0.
So we should be able to find it in 5.4.
5.4 should have it, yeah.
It might just be enable ray tracing.
In 5.7, we changed it to enable ray tracing rather than Osprey because we've added optics, NVIDIA's optics. But previous to 5.7, it should be enable Osprey. And you turn on shadows. No, it wasn't a plugin. It was a plugin in 5.0. Since 5.1, it's been just there. Okay. It may be advanced. So now I turned on shadows, so it looks a little darker at the bottom. Okay. I can kind of go kind of arbitrarily complex. I'm changing the renderer from SciViz, which is a raycaster, to path tracer. So this does a more complete job of computing global illumination. And then I'm changing the appearance of these streamlines. I'm going to give them a material, change it from none to water, and zoom in and increase the number of samples. And so it's hard to see in this display, but now I've got these streamlines, which they look like water. They bend light so you can see things behind them the right direction. You can make them metal to show other things and kind of add arbitrary display properties. Okay. And you can continue on and get fancier and fancier. Like I said, one of the big things in ParaView 5.7 that we're in the process of releasing is that we've added NVIDIA's optics. And if you spend enough time on it, you can make it look really, really good, as Joe and others have done before. If I go to paraview.org and go to videos, my favorite one right now is this one from Jean Favre. It's a CFD simulation, and this was all done within ParaView and Osprey. So this is, if you spend enough time at it and you have very, very nice data, you can make really, really compelling looking videos and images. Okay. Okay. Or in other words, you can add fancy effects and totally obscure the meaning of the data with glam. Okay. Okay. So back to the slides here. So far we've been doing all kind of traditional SciViz, qualitative images of the data. ParaView has quite a lot of expressivity in terms of quantitative aspects as well. So we've been looking at isocontour filter and streamlines and others. But we also have a good set of plotting capabilities, some statistical analysis features which are due for an overhaul, interface to other dedicated languages. So if you follow through the tutorial, you get a good set of controls for, you'll get an understanding of how you can apply the filters like this plot over line, which is the simplest quantitative analysis. Filter, and you can get built-in charts and plots out of ParaView as well. Okay, and again, these plots and charts are all at the VTK level, so they're exposed kind of everywhere. They're BSD, and they run on Mac, Linux, Windows, and so forth. Okay. Volume rendering is well covered as well. So I would turn off Osprey Path Tracer if it's still on. Because its volume rendering is not supported there yet. That's planned for Osprey 2.1 at the end of next year. But you can turn on volume rendering and then cast rays through the data and mess with the opacity and color to get kind of arbitrary effects. Like if you see a MRI or a CT scan, usually these are most often drawn this way in medical visualization. ParaView can do volume rendering, and it can do it at scale, okay, when everyone's rendering a different subset of the data. Okay. I will just show you time-based data. So far we've had pretty uninteresting data. It just has one time step. If you take the time, you can animate along the integration length of those streamlines, and you can make up some some animations from them. But we have good support for time varying data as well. If I do load up the CAN data set, this is another Exodus sample data set from Sandia made 100 years ago. And load all of the variables. This is a time varying data set. You can tell because up here in this, this quick look, we can see that we have 43 time steps here. Or a better way to get that same information is look at the information tab, which tells me that this is a multi-block data set. It came from this file. It has this many cells and points. It takes up 2 megabytes in memory. It has these arrays, some of which are centered on the points, the nodes, some of which are centered on the cells, the elements. Some of them are scalar quantities. You can tell because here in the data ranges we have a min and a max, but only one, so it's just a scalar. And others are vector quantities because we have the min and the max for the x, y, and z component. And furthermore, if we go way down to the bottom of this, this information tab, not only do we see the geometric extent, but we also see the temporal extent. So this data set has time values at exactly 0 and 0.001, etc. But then if we load the data, if we happen to have a time varying data set, kind of the simplest way to inspect it is with a flipbook animation. And you can use these VCR controls up here to step through the time series. I'll loop and I'll animate through the loop. Now I can see the simulation of this can being crushed. And I think it's actually supposed to be this direction. So I got this can, it's being crushed by this block. Okay. And I want to color by the displacement. The block doesn't really change all that much, but the can, of course, gets displaced quite a bit. Okay. In the tutorial, they go into some extent about how to ensure that these color ranges are appropriate to the entire data domain. One of the ways is to say, rescale the color map so that it covers the entire temporal domain. Because it's very important not to have the color lie. So if you set the color ranges at the very first time step when nothing is going on, your colors will be completely meaningless by the last time step. So you can pay attention to that, and we have controls that let you be precise about what you want the colors to do. Okay. Still, we've been doing a lot of qualitative visualization. ParaView has good support for quantitative queries. So under the file, edit menu. Under the edit menu, oh, I was wrong. Under the, let me get my bearings here. Under the edit menu, under find data, I can submit queries. So I want to find all cells where the equivalent plastic strain is greater than, let's see what the equivalent plastic strain range is. Let's say greater than 1.6. Okay. And then run the selection query. And this will give me a list of, this gives me the subset of cells. In this case, it's the entire set. I said less than, I want greater than or equal to. Run selection query. And that should give me just a few cells now. So let's make this bigger. And if I look very carefully, I can see that I've got just a couple of cells here that met that query criterion. Okay. I can extract those. If I search for extract selection, I can apply a filter which is going to pull these cells out, and I have just those cells. Okay. Okay. And you can also do brush-based selection. So above the view, there are a set of icons here which let you paint on the view and extract the cells or points behind your rectangular selection in case you don't know what you're looking for. You just see something in the data which looks interesting, then you can use the brush-based selection to grab it visually and then extract it and then take a look at the data. And you can dive down into the details. Okay. If you really want the details, you can open up a spreadsheet view. And this shows me the exact quantities on the data. So I can see that this point somewhere here has exactly this acceleration, this displacement. Try to zoom in here, make that a little higher. Or I can look at the cells. I found that hexahedron right there at the very end. Sorry, as I mangle the keys around here. And I can step through the data and look for for items of interest and then kind of drill down and look at them. Okay, so that's what selection is all about. It's about extracting subsets where the data is particularly interesting, either that you know a priori what the quantities are or not, when you could do it visually. Okay. So we've been using ParaView locally on data which is small enough to fit into the memory of our laptops here. ParaView is convenient to use that way, but really the design factor that most matters and why the DOE paid us to create it and is because we can split up the data. The reason this works is that most viz operations tend to be trivially parallel. So we have a lot of points, a lot of cells, and a lot of pixels. And for the most part, all of those things can be split up independently and processed independently and computed, and you'll get generally the right result. Okay? So what we do is we take one pipeline, so this goes back to what you said before, we have this one pipeline that you see in the pipeline browser, and we run independent copies of that on all of the nodes in the cluster. Okay? Each of those nodes runs the same pipeline on a different subset of the data. And most of the things in Viz will work just fine. So if I apply a clip along a line, every node can clip its own local data, and you get the result, you draw the result back together, and you get the right results. Some filters don't. Most filters that don't operate properly in parallel independently can be solved by adding ghost cells. So it's a layer of boundary cells around each node's local mesh that are owned by cells remotely. And for those that are completely hopeless, like the streamlines in general, filters can call MPI to talk amongst each other. Okay. Rendering, except in the case of ray tracing is trivially parallel in distributed memory contexts. Every node has its independent subset of the data. We have every node render and produce the color and the depth information at every pixel. And then we combine all the local rasters such that we only keep the color where the depth is nearest among the four, and then we get a globally correct result from that viewpoint. We use a library called ICE-T, which Ken Moreland at Sandia wrote a long time ago, and it's quite fast. It's proven the test of time. It's withstood the test of time. So in detail, this is kind of what ParaView looks like. We split up the data processing in MPI parallel. The rendering can be split up the same way in MPI parallel, and then the client drives everything. Bunch of different modes you can run ParaView. You can split up these different components logically into different sets of processes. But the ones that people generally use are either combined server, where the MPI job on the big machine has the data server, the data processing, and the rendering components split up, driven by some client or some Python script, or in batch mode, where there is no client per se. And it can be very easy to get started with ParaView in parallel contexts. In your copy, go to File and hit the Connect button, and say Fetch Servers. And that's going to grab an XML file from Kitware, specifically paraview.org files PVSC. If you set up ParaView on your home institution and you want us to make it easy for people to connect to it, let me know, and I can put your connection information up here. But once you fetch servers, pick either Cooley or Theta. I think Theta isn't reserved today, so Cooley will work better. At Argonne, either for Windows or not, and say Import Selected. And then once you do that, go to File, Connect again, and you'll be able to click on Cooley or Theta if you pick that. And then you have a dialog that comes up asking you for the specifics of the connection you want. Okay. One of the more annoying options is what on Linux and Mac, Xterm may or may not be available. And if it is, it may be located in a different spot. So you might have to change Xterm executable's path, or just get rid of the path. It might work too. You'll fill in your username, not all capitals, but your actual username on Cooley, and change ParaView version to 5.6.1, v5.6.1.
Is that the version that we have locally?
It should be if you downloaded it. It has to match, the minor number has to match. So if you've got ParaView 5, look at the top bar of ParaView.
I have 560.
You've got 5.6.0, that'll be okay. 5.6.0 will connect to 5.6.1 and vice versa, but it won't connect to 5.4 or 5.7. Okay. You're recommended to use the exact same number, but if 5.6.0 will connect to 5.7, or sorry, 5.6.1. Okay. The account, I think, is ATP-esque 2019 this year. And the queue we've got reserved is this long string. Yeah.
I would recommend just do one node per.
Okay.
I don't know how many, we have enough for everyone.
Okay. So change from number of nodes to reserve to 1. We won't be running in parallel, but that'll be okay. On the number of nodes kind of depends a lot on the queuing policy. On Theta, for instance, on the default queue, you have to have 512 nodes. But if you use the debug quad core or debug flat core, you can do 2 nodes or something like that. But fill in 1 node for our purposes. Okay. If you're on a Mac, you need X11. So you'll need to install Xquartz. They stopped distributing X11 several releases ago. Yes? So the workaround is you could grab a different version of ParaView. So on Mac, in 5.6.0, fetch didn't work. So you could use 5.6.1, or you could grab this file, just open this up in your browser, and then you can copy and paste that into your settings. I can help you with it later.
Mine says I cannot submit to the training queue.
Yeah, this is the wrong queue. You need this one. Yes?
Do you know if the 5.6 guide is also for 5.7?
There isn't a 5. I haven't installed 5.7 yet there.
Okay, so I have 5.7 on my laptop.
Yep.
Then can I? You said though that I thought you said that you could connect to an earlier version.
Just in the just in the patch number. So 5.7 uses a slightly different language.
So where would you copy and paste the map to?
You put that in Mac, that will go under tilde.config ParaView servers.pvsc. Windows, it's slightly different. You need PuTTY rather than X11. And I'll just demonstrate. So reset. So I'm going to File and Connect. I will fetch servers. I'm going to grab Cooley at Argonne rather than Windows to Cooley. And import selected. And then I'm going to click on it and connect. On my case, this is opt-x11 bin. I'm DeMarle. I want 5.6.1. And then once I do that, I get this dialog that says, wait a minute, we're going to try to connect. And we don't want to handle the encryption that goes back and forth, so we pop up an xterm and let you log in as you normally would. And if I type that in, this is telling me everything it did to run the job on the system. You can go ahead and look at these files if you've got access to Cooley or Theta. You can log into the machine and look here and see how I've deployed the connection scripts. And it says that my job is starting. I've got 2 nodes reserved. Still starting. This can take a while, depending on the queue state and how many nodes you've asked for and how many students are trying to get to it. It says I'm running, and so in any second now it's going to connect. And now I'm using ParaView just like I have been all day, but rather than working on my local machine, I can see up here in the pipeline browser that I'm connected to Cooley rather than built in.
Is it much slower?
I'm sorry?
Is it much slower when you run like that?
It can be. There are settings in your preferences. There are settings which determine how much of the work is done remotely and how much is done locally. And so in some cases it can be as fast or faster. In some cases it can be slower, depending on what machine you have and what your settings are. One more thing before I get to your question. So once I've connected, when I say open, now I'm looking at the remote file system. So if I open up soft visualization, and I'm almost done. If I navigate to next to where I've deployed ParaView in the examples directory, I can open up the disk. And it's opening up a file in the remote system, doing the processing there. Load all the variables. And now I have the same disk, but it's at Cooley, or it could have been at Theta. And it can be a very, very large disk if I'm running it at Theta. Okay. One last thing to leave you with is when you're working with with large, high-resolution data on a big machine, a useful thing to know about is the memory inspector. So under Views Memory Inspector, it tells you not only how much local memory does the system have, but for the first few nodes of the server process, how much memory is available versus how much am I actually using on that node. Uh-huh.
Will ParaView either in local or when running remotely make use of GPUs?
Yes, certainly local. Remote, it will make use of them if they're available. On Theta, there aren't any, so we've compiled Mesa, Intel's SWR Mesa, which is reasonably fast to run locally without any GPUs. On other platforms, you can ask for different queues. Like if you ask to run on Titan, you can pick different queues and get different levels of GPU acceleration. Okay. So that's about it. Hope you've got some knowledge now. I hope you can at least be dangerous in ParaView. If you have more questions, I'll be around this evening. You can find me on discourse at paraview.org or vtk.org. And like all the other previous speakers, I wanted to say that Kitware is hiring. So, okay. Thanks.